So let's start. Let me recall what we had the last time. In order to economize the time, I will not rewrite it again. I will just show the blackboard of the previous lecture. So let me recall that the following definition: if you have a random variable eta which takes values, which take natural values, then by p eta we denote the vector of such form, where component number j of this vector, this is just the probability that eta equals to j, and such vector is called distribution of the random variable eta. Okay. So next, let us consider some Markov chain, xi0, xi1, and so on, and then let us this is a Markov chain on some state space X, and let us enumerate elements of this state space just by natural numbers. I recall that our state space always have at most countable cardinality. So and then let me call pk distribution of the random variable xik. So here component number j of this vector is the probability that xik equals to j. So it means that this is a probability that at time k I am sitting at the position j. Okay. Then our goal actually is to learn how to compute this transition, this distribution pk. I introduce the next object, which is called the transition probability matrix. So this is a matrix which is built from the transition probabilities. So at the position number ij, I have the transition probability from the state I to the state j. Okay, and I have for each moment of time I have its own transition probability matrix. Right. So for the moment of time n, this is Pn, which is written on the blackboard. So, and we finished with formulating the lemma, which states the following. If I wish to compute the distribution of my Markov chain at a moment of time k plus n, then it suffices to, so I can compute it in the following way. If I know the distribution at the moment of time k, I just should multiply it to the right subsequently by the transition probability matrices at moment of time k plus 1, k plus 2, and so on at the moment of time n. So now I'll prove this lemma, and I think so. Let me change my screen. Just a second. So I decided that it's better to write down different blackboard. Okay. Oh, okay. So do you see this new blackboard, right?
Yes.
Yes.
Perfect. So let me write down lemma again. So this is a lemma number 6. If I have Markov chain xi0, xi1, xi2, etc. Then Pn, this is distribution of this Markov chain. So it's a vector with components Pn1, Pn2, etc., where Pnj I recall again that this is a probability that psi j, that psi n, so that at the moment of time n, I am sitting at the position number j. So at time n. And the lemma states that that if I wish to compute the distribution of my Markov chain at the moment of time k plus 1, I should take its distribution at the moment of time k, and then multiply it to the transition probability matrices pk plus 1, etc. pn. So proof actually is very, very simple. So let us take any m which is more than or equal to 1, and then let us write the distribution of my Markov chain at the moment of time m and its component number I. How? So by definition, this is the probability that psi m equals to I, right? This is such probability. But then I can write it in the following way. I can write it as a sum over all j from my state space X, probability that psi m equals to I, conditioning at the event that psi m minus 1 equals to j. And also then I should multiply it by the probability that psi m minus 1 equals to j. Why is it so? Why is it so? This is just a law of total probability. Law of total probability. In Russian, this is формула полной вероятности. Формула полной вероятности. Why is it? Just look, because my space of elementary events, it can be represented as a disjoint union over all j from my state space X of the events of such form. So the event consists of those elementary events on which the random variable psi m minus 1 takes value j. So you see, because the random variable psi m minus 1, it should take, I mean, some value, right? So I can represent all elementary events, the set of all elementary events in such form. So just separate the events on which my random variable psi m minus 1 takes fixed value. And then you see that this is exactly the formula of total probability. So okay, then I continue this line. What is this actually? This is just the transition probability at the moment of time m from the state j to the state I, right? And this is exactly the distribution, the component number j of the distribution of my Markov chain at the moment of time m minus 1, right? And I forgot to write down the summation. So here I have the summation over all j from X. But what is this? This is exactly the vector p m minus 1 multiplied by the transition probability matrix at the moment of time m, but then I should take its component, let me move it slightly, its component number I, right? So here I will always understand vectors as rows, not as columns. So I will multiply vectors from the right to the matrices. So this means that that the distribution of my Markov chain at the moment of time m, so look, this equals to this. It holds for all I. So it means that the distribution just equal to Pm minus 1 times the transition probability matrix at the time m. And then the proof follows by induction. You see? So to get the distribution at the next moment of time, I should just multiply by the transition probability matrix. By the transition probability matrix, and then I get this result. So and then by induction. Okay. So this is done. I agree.
Yes.
Mm-hmm. So corollary number 7. Okay, let me first write down some notation. So I recall that if my Markov chain is homogeneous, that is, its transition probabilities does not depend on time, then I use the following notation. I denote the transition probabilities as in the following way. So I do not write this n, which corresponds to the instant of time, and I put this I and j as sub indices. Then the transition probability matrix, it does not depend on time, and I denote it just by large P, by capital P without the subindex n. And this transition probability matrix, this is P, this is M. This is M. Markov chain. The transition probability matrix has the following form: P11, P12, etc. P21, P22, etc. etc. I recall that this metric can be infinite if the number of states is counted. And then corollary 7 of the previous lemma is that for homogeneous Markov chain, Pn equals to the distribution at the moment of time n equals to the distribution of the moment at the moment of time 0 to the power n. You see? So this is indeed trivially follows from this result. Okay, so now once we know the transition probability matrix and once we know the initial distribution, we can compute everything. We can compute the probability where we are situating at the moment of time n. So let me consider some example. So let us consider the following Markov chain with 3 states. Actually, in exercises, I will often, I think, meet Markov chains with 3 states, because with 2 it's really trivial. With 3 it's slightly more complicated, and already there are some things to discuss. So I draw the transition probabilities 1/2, and then 2/3. And also, okay, so it is okay, except that here I should also have the arrow from 3 to 3, 1/2. So let me write down the okay, and also to define completely the Markov chain, I should specify the initial distribution, right? So let me choose it in the following way: 1/3, 2/3, 0. Then I wish to write down the transition probability matrix. So this is a homogeneous Markov chain. The transition probability matrix looks like that. So I cannot go from the first state to the first state. So here I have 0. From the first state to the second state, the probability is 1/3. From the second state to the third state, from the first state to the third state, the probability is 2/3. Then from the second state to the first state, I cannot go. 1, and finally from the third state to the first state, it's 1/2. From the third state to the second state, I cannot go, and here from the third to the third, 1/2. So this is a transition probability matrix. Right. So now I wish to compute the distribution at the moment of time 2. So let us do this. This is a very simple computation. By the lemma, this distribution equals to the initial distribution times the transition probability matrix squared, right? So and here just attention, because I realize that the students have intention to take square of this matrix. I mean, this is of course correct, but this is complicated because you have to compute nine components, right? And then you have to multiply these 9 components by this vector. It's much simpler just to do the following. From the computational point of view, it's much simpler to compute it in such a way, right? So let us do this. Because like that you will have to compute only 3 components, and then again 3 components, so 6 instead of 12 operations. Okay, so what should I write? So pi 0 times the transition probability matrix. This is here I have 0, right? Here I have 0. Then here I have a 1/9, and here I have what do I have? I have 1/3 times 2/3, it's 2/9 plus 2/3 plus 2/3, it's 8/9. It's 8/9. Oh, we should multiply it by p again. Actually, what is this vector? Who is this? Who is this?
P1.
Yeah, this is exactly the distribution at the first moment of time. But look, in fact, instead of computing this 8/9, I understand that the distribution is such that sum of its components equals 0. Right? Sum of the components of the distribution equals 0. Oh, sorry, not 0, 1, because these are the probabilities. So I could directly write that here I have 8/9. Okay, and this equals Well, let us finish this computation. This is 8. This is 4/9, right? 4/9. Then 1/3 0, right? And then okay, 5/9. It should be 5/9 because of this. Because of this, I even do not want to compute. So this is the distribution of the second moment of time. So the probability, if you start with at the position 1 with probability 1/3, at the position 2 with probability 2/3, then at the probability to be at the second moment of time at the position 1 is 4/9, and at the position 3 is 5/9, and at the position 2 is 0. Indeed, it's easy to see that the probability to be at the position 2 is 0, because here, I mean, I cannot start from the third position, right? Because the probability is 0. And if I start from the first or from the second, if I start from the first, I mean, so I can go to the second position only from the first one. So it means that at the moment of time 1, to be at the position 2, I should be here. I should be here. But if I start here, I cannot be here at the moment of time 1. And also, if I start here, I cannot be here at time 1, right? It's possible only if I start there. But I cannot start there because I have 0 here. So in such a way, just you can check your computations. So now it's indeed clear that here we should have 0. Okay. Just a second. Okay. So now let me note the following thing. Look, I can write down the distribution at moment of time n, in the following way, according to the lemma I've proven, right? But what is this? Let me write it as follows. Sum over all elements A of my state space P n A dot. This is the row number. This is the row number A of the matrix Pn. Indeed, just when you multiply the vector to the matrix from the left, sorry, you multiply the vector to the matrix from the right, then you should sum the components of this vector multiplied by the rows of the matrix, right? Okay, so let us remember this, and let us do the following thing. Let us consider a Markov chain with the same transition probability matrix P. Okay, so let me just to simplify my further life, write transition probability matrix like in the following way. This will be always from now on transition probability matrix. probability matrix, because it's too long to write every time transition probability matrix. So I consider Markov chain with the same transition probability matrix, but the initial conditions will be different. Yeah, I will call this Markov chain eta 0, eta 1, etc. And also I will put above eta the letter A. I will explain what is this letter. Actually, this is a number of a state, and an initial distribution. I will consider the following: P0 J equals to delta AJ. So this is a Kronecker delta. So it equals to 1 where A equals J, and it is 0 when A is different from J. In order to underline that all this dependent from A, I put here the upper index A, and also I'll put my A here. So then I will denote by P and A. Similarly, distribution of my Markov chain eta and A. Okay, so what is this? This is just the same Markov chain in the sense that it has the same transition probabilities, but the initial condition, the initial distribution is different. Here I had some initial distribution P pi 0, and now I have initial distribution such that with probability 1, I am sitting at the position number A. Okay, and for each A, I consider its own Markov chain for each A from X. Then let us compute this distribution. This distribution by the lemma. This is the initial distribution times the transition probability matrix to the power n, right? But the initial distribution, this is a vector. This is a vector which has everywhere zeros except the position A. Except the position A. And I multiply it to the right by the matrix Pn, and what I obtain exactly the row number A of my transition probability matrix to the power n. Okay. So look.
Sorry, you have a typo at first equality. There should be P0A instead of Pn0.
P0A,
Yes.
where?
First equality at the last row.
Thank you. Yeah, you're right. Thank you. P0A, yeah, right. So look, and then let us look here. From here we get that Pn, from here and from the last equality, we get that this Pna, right? This is just the distribution of my Markov chain with initial condition where I'm starting at the position A. So I can write down this formula as sum over all A P A 0 0. This is 0. and then the distribution of my new Markov chain with the initial condition A. So this is a vector, right? This is a vector. This is just a number. So look, actually, what is this? This is like decomposition over basis. Because I'm interested in distribution of my Markov chain where when the transition probabilities are fixed, but the initial condition is some. So I have fixed transition probabilities and I have some initial condition. And I wish to understand how the Markov chain behaves. I'm interested in its distribution at the moment of time n. Then what can I do actually? I can consider for each state its own Markov chain, which starts with probability 1 from this state. Study its dynamics, obtain its distribution at the moment of time n, and then the dynamics of my initial Markov chain with the initial distribution pi 0 will be obtained like as a linear combination of distributions of these Markov chains with fixed initial conditions. So in fact, what does it mean? It means more or less that if you wish to understand how the Markov chain behaves, it suffices to consider only initial conditions of such form, of that form, right? So this like you decompose your stochastic process to some basis stochastic processes with deterministic initial conditions, because this initial condition is deterministic, you see, so there is no randomness here. You are sure that you start from the position A. Is it clear?
Yes.
So we will sometimes use this idea. So actually it means even more than I have written here. If you wish to understand what is going on with your Markov chain, it's always suffices to study what is going on with your Markov chain when your initial conditions are deterministic, but you should look at all possible deterministic initial conditions. Okay, so now let us note the following thing. Let me return to my lem or to my corollary, for example, to this one. And let us note the following. Actually, when I'm constructing Markov chain, I can choose any transition probabilities, right? Any transition probabilities in such a way that their sum over second argument should be equal to 1. They should be non-negative, and then I can choose any distribution, any initial distribution. Then I'll obtain Markov chain, and then I can compute accordingly to this corollary its distribution at the moment of time n. What does it mean? It means that if I take any transition probability matrix and I multiply it to the left by any distribution, I will always get a distribution. So this guy is a distribution, right? Distribution, it means that sum of its components equals to 1. So actually, it's some special property of these matrices. And let us discuss in this context matrices of such form. These matrices actually are called stochastic matrices. Stochastic matrices. Now let me give an accurate definition. Stochastic matrices. Definition. A square matrix is called stochastic if let me let me denote this matrix somehow. Let me denote it by A, and it should has components A small ij. If the sum of its components over the second argument equals to 1, and also all components should be non-negative. Should be non-negative. So look, any transition probability matrix is stochastic. Moreover, any stochastic matrix is a transition probability matrix for some Markov chain, because you can just take arbitrary initial distribution, take this stochastic matrix for the transition probability matrix, and that's it, right? So this property that the sum over what is this actually? This is the sum over row, right? This is sum over row. This is the property that the sum over row equals to 1. This is exactly the property that the transition probabilities, the sum over the second argument equals to 1, right? So for example, this matrix is stochastic. So actually, it means that there is the following interplay between Markov chains and linear algebra. Just studying of stochastic matrices. This is just the same that studying of Markov chains. For example, we'll prove famous Perron-Frobenius theorem. Perron-Frobenius theorem. This will be later. And actually, this is a theorem which states some assertion about some special but natural kind of matrices. And this will be done by stochastic methods. So you see, you can get results in linear algebra using just probability theory, and you can get results using in the probability theory using linear algebra. So sometimes the first way is more convenient. Sometimes the second way is more convenient. So let us discuss some properties of stochastic matrices. I mean, this is simple and not very interesting, but I think that it worth to be mentioned. So I will formulate several assertions, but I will not prove them. I will leave them as exercises. I will need some notation. Sorry. Some notation. So vector f with components f1, f2, etc. is called non-negative. If all its components are non-negative. So very simple definition. And I will write f more than or equal to 0. actually, along this course, almost always, when I'm writing vector, I will understand it as a row, as I've already told. So let me write it somewhere here. Always row vectors. Always row vectors. This is the first notation. And what is distribution? I have already defined it, right? What is the distribution? Yes, I have already defined it. So let me just let me recall it here. F is called vector f1, f2, etc. is called distribution or probability distribution if it is non-negative and sum of its components equals to what? To what? Who is still listening?
1.
1, right. Okay. So lemma. This is lemma number 8. Lemma number 8. The following 3 assertions are equivalent. So the first assertion is following. A is stochastic matrix. So sum of its elements over O equals to 1, and all its elements are non-negative. The second assertion is slightly more complicated. So A multiplied, I can multiply to the right or to the left. It isn't important, but well, I would multiply it to the right. If I multiply it to the right, I should put transposition, because as I told, my vectors are strings, are row vectors, and this should be a non-negative vector for any non-negative f. And simultaneously, if I multiplied my matrix A to the right by the vector 1, where this will be a column vector, which consists only on units 1, 1, 1, 1, 1, then I should get again the same vector 1. Actually, this exactly means that the sum of elements of the matrix A over the row equals to, over each row equals to 1. In other words, 1 is the right eigenvector with eigenvalue 1. And the third property is the following. If vector mu with components mu1, mu2, etc. is a distribution, then mu multiplied to the right by the matrix A is again a distribution. So actually, the third assertion is what we saw in our lemma about the distribution at the moment of time n, because what we had, we exactly we have taken a distribution multiplied to stochastic matrix. Okay, this is a question why the matrix to the power n is stochastic, but the next lemma which I'll formulate will say exactly this, that this matrix is also stochastic. And then I get again the distribution. This is exactly the situation of the third item of my lemma 9. So let me formulate one more lemma, lemma 10. If A and B are both stochastic matrices, then AB also is stochastic. So this is why in particular the transition probability matrix to the power n also is stochastic matrix. So are there some questions? Are there any questions concerning this part?
Professor, can we say maybe that the inverse is also a stochastic?
Sorry?
That the inverse of a stochastic matrix is stochastic also,
No,
or not?
No,
Okay.
definitely not. It shouldn't be like this.
Sorry.
Wait.
In point 3, if a vector is a what word?
If vector is a distribution,
Thanks.
Mhm. Concerning the inverse matrix, this is a very good question. It is related to one of problems I suggested you to solve. And if you have taken a look on these problems, there was one, the following: if you have a Markov chain xi0, xi1, xi2, etc., say till moment of time t, then what can we say about the inverse sequence of random variables? What can we say about this inverse sequence? Does it form a Markov chain or not? And I mean, it seems to be related to the question about the inverse matrix. So once you solve this problem, you can think about the inverse matrix to the transition probability matrix. Okay, so the next rather fundamental thing which I wanted to talk about is Markov chain in n steps. In n steps. So I have the following question. Okay, so I think that this is more or less the last like computational and boring thing. Further on, it will become like more less computational and more interesting, I hope. But these are some fundamental things I have to speak about. Look, assume that we have a Markov chain, xi0, xi1, xi2, etc. This is some Markov chain. And for simplicity, I will assume that it is homogeneous. This is indeed for simplicity, just for simplicity of notation. So, but pi be a transition probability matrix of this Markov chain, and I ask the following question: if the following matrix, if the following sequence of random variables is Markov chain or not. So what does it mean? I mean, I have my frog. I have my frog which jumps from one position, from one state to another with some probabilities in this Markov chain. For example, it jumps each second. But I don't want to look at my frog each second. I want to look at my frog each minute. What does it mean? It means that I wish to look at its position at time 0. Then I wish to look at its position at time 1 minute. It means at 60 seconds. Then psi 120, etc. So it means that just I ask the question I posed with n equals to 60. What can I say about this stochastic process? Should it be Markov chain or not?
Well, then you transition probability matrix will be pi
Yes.
in the power of n.
Exactly. This is absolutely correct. So lemma 11 the sequence psi 0, psi n, psi 2n, etc. is a Markov chain with the transition probability matrix p to the power n. Okay, so it looks very natural, but still it requires some proof. Okay, this is a word sequence. Let me rewrite it. Before starting the proof, let me recall you the following thing, which I mean this is a very elementary thing from the first year of education, but I realize that often people do not know this. So let me formulate it. That A1 be a matrix with components A, I, J, 1 above. A2 similarly be a matrix with components A, I, J, 2 above. A3, etc. B till an. I need finite number of matrices till an. B matrices square matrices of the same size. Then I have the following simple relation. If I wish to compute its product and take its element number ij, then this is just the sum over all L1 n minus 1 A I L1 up A L2 L3 A L3 L4 etc. A L
Sorry, I
n
think
minus
we have again typo, because the second term, it seems that it should be a L1, L2.
Yes, thank you. It's correct. This is correct, Camille. Yes. Okay, let me write it. So actually, this moreover, this is A1 above. Here I have 2. So L1, L2, etc. A Ln minus 1 J. And this is the last matrix. The last matrix. Okay. So this is a formula. This is just the generalization of the formula of the product of two matrices, right? For the case when you have, instead of 2, you have n matrices. I will not prove it. I will leave this as an exercise. Instead, let me prove my lemma 11. Proof of lemma 11. So how do you suggest to prove it actually? How do you suggest to prove it? So we need to check that the sequence is a Markov chain. So it means that we should check one of the two possible definitions. Which definition would you check actually?
With P0 multiplied by product of all transitional probabilities, because you can combine and every n transitional probabilities in one transitional probability of a new Markov chain.
Yeah, I think that I mean it isn't very clear what did you suggest, but I think that you suggest more or less what I'm going to do actually. So I wish to check the second definition of Markov chain. Let us check definition 2. Definition 2 of Markov chains. I recall that this definition was about the following probability, about the probability that psi0 equals to sum I0. Then the next element of my sequence is psi n. This should equal to I. Let me write here In, and so on. And then psi, say k times n equal to I k times n. And I should show that this probability equals to the initial probability to be at the position I0 times the transition probability of my new Markov chain, if this is a Markov chain indeed, to pass from I0 to In, and so on and so forth. But how can I compute such probability? Just in the following way, I can take a sum over all say L1, Ln minus 1. Let me write here 0 from x, then L2, sorry, L1, 1, Ln minus 1, 1 from x, etc. And here I have the probability that at xi0 I am at I0, then at xi1 I am at L10, at xi2 I am at L20, and so on. At xi n minus 1 I am at Ln minus 1, right? Let me move it. At Ln minus 1, 0, at xi n, I should be in in. Then at xi n plus 1, I should be at L11, etc. Okay, so I hope you understand what do I mean. I mean that I take the summation over all intermediate states. So overall, so here only positions number 0 at time 0, at time n, etc. are fixed, but I fix the positions between these times and I sum over all these positions. Okay. But then I can write down this probability directly, each such probability, because I know that my initial sequence xi0, xi1, and so on, this is a Markov chain. So I have summation of the same form, and here I have initial distribution, its component number I0, then transition probability from I0 to L10, then the transition probability from L10 to L20, and so on. Finally, I have transition probability from L0n-1 to IN. Then transition probability from IN to L to L1, 2, etc. But look, when I take the summation, this summation, only these guys will be changed when I change L10, etc., Ln-10. So when I will take this first summation, I will get exactly term like here. So I'll get exactly my transition probability matrix P to the power n, and its component I0, this one, IN, this one, and so on, and so on. So finally I get initial distribution at the position I0, then pi n transition probability matrix to the power n, its components I0, IN, then its component I2n, etc. So, and this means that our sequence is indeed a Markov chain with transition probability matrix, as claimed, p to the power n, because I mean the component of the transition probability matrix number I0, IN, this is exactly the transition probability from the position I0 to the position IN. Okay, so are you agree, or are there any questions? Are there any questions? Okay. So let us denote by P and Ij transition probabilities of the chain of the Markov chain xi 0, xi n, xi 2n, etc. The Markov chain in n steps, which we have just proven, that this is indeed the Markov chain. So corollary. Corollary, let me call it corollary 12, which we have is that, okay, so I mean, this isn't even the corollary, this is just the notation, right? But, well, let me call it corollary. That these transition probabilities have the following form. This is the initial transition probability matrix to the power n and its component number ij. And then we have the following one more trivial corollary. You see, everything we are doing is completely trivial. But then it turns out to be very useful. The following corollary, if you consider transition probability in k plus n steps, then it can be obtained in the following way. You should sum up over all states transition probabilities in n steps and multiply it by the transition probability in k steps, and you sum up over this intermediate position. So what does it mean? It means the following. If you wish to pass in the position I to the position j in k plus n steps, then you should arrive somewhere in k steps and then go from this position in n steps. But I've written it in a different way, right? So first n and then k. So you should arrive to some position L in n steps and then go from this position in k steps, and then you should sum up over all these intermediate positions L. Actually, this seems to be something trivial, but this is the very important property of Markov chains, because such property holds only for Markov chain. I mean, for general stochastic process, it doesn't hold. Because where is this Markov property is sitting? It is sitting in the fact that once I arrived to the position L, it isn't important how exactly I went from the position I to the position L. The only thing which is important is that finally I am at the position L. And then to get to the position J, I should know only the transition probability from the position L to the position J. Okay. And this is like trivial but very important equality, and this is so important that it has special name. It's called Kolmogorov-Chapman equation. Kolmogorov-Chapman equation. Actually, if you study Markov processes with continuous time, which are much more complicated that we are doing, you will find there also some fundamental theorem which is also called Kolmogorov-Chapman equation, which looks much less trivial than what I've written down here. But this is exactly the same. In fact, this is exactly the same. So I will not often use this Kolmogorov-Chapman equation, but I would like that if once you meet it somewhere else, then just recall this equation, and you understand that this is completely intuitive and simple. Okay, so proof of this corollary. I mean, the proof is trivial because the left-hand side is according to corollary 12, according to corollary 12, the left-hand side equals to p to the power k plus n, and the right-hand side equals to sum over L from X. Here I should write ij sum to the power sum over all states X, p to the power n, its element number il times p to the power k, its element number, sorry, not ij, il, lj. Yeah, and this equality is true because this is the same that writes that p to the power k plus n equals to p to the power n times p to the power k. This is true. Okay. Do you have any questions or comments? So now let us summarize what we have for the moment. For the moment, we know what is Markov chain. We know two definitions of the Markov chain, and we can prove their equivalence, right? Second, we understand how to compute the distribution of the Markov chain at arbitrary moment of time once you have transition probability matrix and the initial distribution, right? Third, we understand that analysis of Markov chains is the same as analysis of stochastic matrices. And fourth, we understand that Markov chain in n steps is again a Markov chain, and we have such nice corollaries. So basically, we know everything about Markov chains in finite times. So since we can, given transition probability matrix, we can compute the distribution of the Markov chain in arbitrary moment of time, it means that just we know everything for finite times. So that's why our next step is to look at some examples, and then to pass to the following question: what happens when time goes to infinity? At the end of this lecture and the next lecture will be devoted to some examples, and in one lecture we will talk, I think that this will be in one lecture, we will talk about the behavior Markov chain when time goes to infinity. At least we start to talk about this. Okay, examples. So the first example is random walk. Examples, let me write it like that. Examples, random walk. What is a random walk? So the simplest version of random walk is the following system. Let us consider, say, natural numbers, 0, 1, not natural, entire numbers, -1, -2, 2, 3, and so on. And then we are doing the following. We are sitting at some of the numbers, say at 0. Then we toss a coin. So бросаем монетку, значит, орел или решка. We toss a coin. We have head with probability p, and tail with probability q. So p plus q equals to 1. Значит, орел с вероятностью p, решка с вероятностью q. Значит, очень хорошо. And then if I have head, then I go to the right by 1. And if I have tail, I go to the left. So it means actually, so I'm sitting at a given position, and then I go to the right with probability P, and I go to the left, and I go to the left with probability 1 minus P, which is Q. It's probability Q. Okay. Such simple story. Here we can ask various questions. We can ask the following question. For example, we are playing. We are playing in this game, and if we have head, then you pay me 1 ruble. If we have tail, then I pay you 1 ruble. And if and the initial moment of time I have, say, m rubles, you have n rubles, and the question is with which probability I will not be able to continue playing this game in some time because I'll become bankrupt, so I will not have any money, and with which probability this will be you. So давайте повторю на русском, что я не хочу это писать. Значит, мы играем в орлянку на деньги. Значит, у меня есть там 10 рублей, у вас есть 20 рублей. Ну и вопрос, с какой вероятностью я, так сказать, первый обанкрочусь, с какой вероятностью вы первый обанкротитесь. Значит, actually, the system is a Markov chain. I mean, this is intuitively, it is just obvious because when my next position is clearly depend only on the result of the coin, if I have head or tail, and on my present position, right? So this is clearly a Markov chain, and it doesn't depend on the past. So the future depends only on the present position, but does not depend on the past. But nevertheless, let me once rigorously prove that this is indeed the Markov chain, and let me construct a mathematical model of this story. So what do we have? We have initial position. So this is initial position. This is of course random. This can be random. It belongs to Z, right? This entire number. Then I have results of my tosses of the coin. So I have random variables I, J, which equal to 1 with probability P, which equal if I have a head, and which equal to -1 with probability Q if I have tail. So here I have written shortened notation for the following. Equals to P, probability to eta J equals to -1 is Q, and all eta J are independent. And also they are independent from the initial distribution. They are independent from the initial distribution xi0. Then how should I construct the process xi(n)? Xi(n), this is position at time n. So who can say how should I construct this xi(n)? I want to use the initial distribution and these random variables eta J, which describes the result of my coin.
Initial distribution plus sum of all eta J's.
Yeah, so this is xi0 plus just sum over J from 1 to n eta J. And proposition 14, the random process xi0, xi1, etc. Is a Markov chain. Is a Markov chain. So proof. Now, again, like I can check one of two possible definitions, and now let me check the first definition. It will be simpler. Let us check definition 1 of Markov chain. Markov chain. So what should I prove? That is I wish to show that the following equality holds, that the probability psi n equals to certain in, conditioning at the event that psi n minus 1 equal to certain in minus 1, psi 0 equals to certain I0. This should be equal to similar probability, but when I conditioning only on the present state, that is on the position at the moment of time n minus 1, right? So I should prove this. Okay. Let us consider the first probability. I will not rewrite it. I will write down just directly like this. What is written down here? What is psi n actually? Psi n, this is exactly psi n minus 1 plus eta n, right? By definition of my Markov chain. But then, look, here I have condition that psi n minus 1 equals to in minus 1. This means that this probability will be non-zero. Okay, let me maybe write it in more details, like that. No, even I would write it. I would write it like that. Eta n equals to in minus psi n minus 1, right? So I just replaced psi n by this sum, and I put psi n minus 1 to the right. Psi n minus 1 equals to in minus 1, etc. Psi 0 equals to I0. But look, psi n minus 1 fixed, because I have this condition. Actually, here I skip some formal step, but let me leave it as an exercise. I will directly write that eta n equals to in minus 2 minus in minus 1, conditioning at the event that psi n minus 1 equals to in minus 1. So I need another 3 minutes, I think, to conclude. Psi 0 equals to I0. Look, here, I mean, intuitively, it's clear what is written down, because just I take conditional probability, conditioning that psi n minus 1 equals to in minus 1. This means that this psi n minus 1 must be equal to in minus 1, and then I replace it here by in minus 1. But mathematically, I mean, maybe this is not so clear. If it is not clear for you, then just spend 5 or 10 or 15 minutes to understand why this is true. This directly follows from the definition of the conditional probability. Okay, then this probability, I claim that it equals to the probability that eta n equals to in minus 1. Why this is so? Just because eta n is independent from psi n minus 1, psi 0. Because look, psi n minus 1, because my etas first, they assumed to be independent from psi 0, and second, all etas are independent between each other. And these random variables, they are formed using psi 0 and etas 1, 2, 3, etc. till n minus 1. And here eta n doesn't have I mean eta n isn't used to construct this psi 0 psi n minus 1 because of this formula and then since eta n is independent from eta 1 etc eta n minus 1, then it is independent from these guys. And if we have two independent events, then the conditional probability equals to the probability without conditioning. But well, then this probability, what is this? This is just P if in minus 1 is 1, right? Q if in minus 1 is minus 1, and this is 0 otherwise. This is 0 otherwise. Okay. So we have just computed explicitly this first probability. But then what we are doing? Then we write down the second probability, the probability that psi n equals to I n conditioning at the event that psi n minus 1 equals to I n minus 1. And we do exactly the same argument. Look, in this argument, actually, I never used this tail. I used only that psi n minus 1 equals to I n minus 1. That's why when I write this probability, I'll get similar relation as here, but I will not have the conditioning. I will have the conditioning only this one, that psi n minus 1 equals to I n minus 1, right? And then I'll get that these events are independent. I'll get exactly the same. So this argument will lead me to exactly the same formula. This means that these probabilities are equal, and this means that we have checked the definition of the Markov chain. Actually, in the definition there were two items. The first item stated this equality, and the second item stated that this probability equals to the transition probability. But since here the transition probabilities wasn't claimed to what are they equal, then it means that we have proven that the definition. I mean, we have proven that our sequence is a Markov chain. Okay, is it clear or not?
Yes.
Mm-hmm. So and actually, what are the transition probabilities? These are exactly the transition probabilities. This equals to pi I n minus 1. The probability to pass from I n minus 1 to the position I n. Right? So the last thing I want to do, I want to write down the transition probability matrix of a random walk. It has the following form. Look, this should be 3 diagonal. The main diagonal is 0. The main diagonal is 0, because if they're equal, then I have 0, 0, 0, 0, etc. Above the main diagonal, this is this situation. I have P, and below the main diagonal, I have Q. And everywhere here I have zeros. So this is transition probability matrix. So I recall you that all our matrices can be of infinite size, and everything we were doing today, matrices also could be of infinite size. Everything was true for infinite matrices, right? Okay, so if you do not have questions, then let us finish.
Excuse me.
Yeah.
You build a matrix infinite only in one side, but it should be infinite in both sides. Otherwise, in the first row, you'll get sum of all elements equals P, but it should be equals P plus Q.
Sorry, could you repeat? Okay. So this should be infinite in both directions, right?
Yes.
Yes, you're right. So let me. Yeah, indeed. You see that transition probability matrices the sum of over each row should be equal to 1. The sum over each row should be equal to 1. But here if I have such corner, the sum is just P. I mean, it isn't 1. What is the problem? The problem is that if I how it was drawn before, I had the first state, and from the first state I had the probability to leave it with probability P, right? To the right and to the left. I didn't draw any probability to go to the left, so it isn't correct because I mean it would be correct only if P equal to 1, right? But in general, P is different from 1. That's why I should also have probability to go to the left with probability Q. It means that I should continue this matrix in this direction. Another possibility is, I mean, you can slightly change. So if you have such a random walk, you can slightly change your transition probabilities at the boundary of this Markov chain. So here you have P, 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 Q, 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 and here you can for example assume that once you are in the first state, then you stays here with probability 1 minus P, which is actually Q, and here you can also assume that you stay here with probability 1 minus Q, so which is actually P, right? So in your homework we will have Markov chains of such form. Okay, so the next time we will start with discussing Galton-Watson model. This will be, I think, more interesting and more complicated. There I will formulate and prove some non-trivial result. I think this will be the first non-trivial result in my lectures. Okay, so more questions, or we should finish. So if you don't have questions, then let us. Okay.
Thank you.
So,
Bye, Professor.
bye.